You can also put imaginary numbers into other functions, and I'll in particular talk about exponentials. So it's in particular possible to take something like the exponential of I times a real number x. If we go back to a Taylor series representation of what an exponential is, an exponential is just an exponential Taylor series is of e to the alpha is 1 plus alpha over 1 factorial, alpha squared over 2 factorial, plus alpha squared over 3 factorial, alpha to the 4th over 4 factorial, and so on. I'm going to compute this out a little bit, but rearrange some terms. Some terms here are going to be real, because they're either going to involve a square of I, or a 4th power of I, or a 6th power, or any even power of I. Some terms in this series are going to be imaginary, because they're going to either involve I, or I cubed, or I to the 5th. All of those end up having an extra factor of I. So this works out to be sum 1 minus x squared plus x over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Plus I times the sum x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and then so on. There's odd powers of x in this sum. So this just comes from, again, the definition of what the Taylor series is for an exponential function, and segregating real and imaginary parts of this. And if you recognize these sums I put in parentheses here, this is none other than cosine of x in this first parenthesis. In the second parenthesis is just sine of x. So that's a very general thing that we should remember. Now the complex conjugate of this, again, comes from just taking I and putting in minus I. That would be that. And in this side of the expression, if I switch I with minus I, it doesn't change the real part. It just changes the imaginary part. Notice that the absolute value of something like e to the I x or e to the I theta will equal 1. And that's because this thing will equal the real part squared plus the imaginary part squared. So remember that a cosine squared of an angle plus the sine squared of an angle is always equal to 1. But that's actually comforting. Because the norm squared of an angle of a complex number is supposed to equal it times its complex conjugate. And this is equal to e to the I theta times e to the minus I theta. And this is supposed to equal e to the 0. Because when I have the product of two exponentials, it's equal to the exponential of the sum of the two exponents. So this particular exponential of an imaginary number is kind of special because it always has a unit length or a unit norm. Let's take some particular cases. E to the I times 0 just equals 1 because that's equal to cosine of 0 plus I times sine of 0. E to the I pi equals minus 1. That's because it's equal to cosine of pi, which is minus 1, plus I times sine of pi, which is 0. E to the I 2 pi equals 1 again. E to the I pi over 2 is purely imaginary, has no real part at all, because cosine of pi over 2 is 0, plus I sine of pi over 2, well, sine of pi over 2 is 1. E to the I 3 pi over 2 is minus I. And in general, I can just compute anything exponential of I times any number as the cosine of that number plus I times the sine of that number. So you should try computing a couple cases. What, for example, is e to the I pi over 4? Or e to the I 3 pi over 4? Well, this routing is root 2 over 2 plus I minus root 2 over 2. The second one is minus root 2 over 2 plus I times root 2 over 2. So the real part is negative, but the imaginary part is still positive.